Hello again, and welcome to our fourth and final lecture on matrices and linear equations. I'd like to spend this lecture showing some applications of the ideas we've developed in the previous lectures. The applications or the ideas of matrix multiplication and determinants and linear systems. Now, I'll be upfront with you. A lot of these applications might look very, very simple, like, gee, do you really need all that power to do that application? But my point is to illustrate modeling techniques, sort of the basic idea of some applications. Real-life applications are much more complicated, and we would not have time to do a real-life application in the short period we have in one of these lectures. But again, you'll get an idea of how scientists work with linear systems and matrices. Now, the first application I'm going to look at it's not really an application in the true sense, but rather it's one way to solve linear systems, another way of solving linear systems, in fact, that uses determinants. I'd like to show you this method. It's called Cramer's rule, and it's a fascinating method. When I was a student, when I was much younger, we solved our linear systems of equations with Cramer's rule all the time. It was a very common technique. So I'd like you to look at this technique when I bring it up here and talk about it, and ask yourself, do you like it? Is it a good method? Remember, given a system of linear equations, we can solve it with that Gaussian elimination technique. But here's another technique, and again, it uses determinants. It's named after Gabriel Cramer, who lived in the 1700s. And here's how it works. I'll explain it as usual with a simple 2-by-2 case, but it works for an arbitrary n-by-n case. In other words, if you have a system of n equations and n unknowns, the same number of equations and unknowns, here's how Cramer's rule works. Well, let's focus on the 2-by-2 case. I'll have two equations. The variables will be x and y. And the constant on the right-hand side, I'm going to use some new letters here, c sub 1 and c sub 2. It'll make the notation easier. And the coefficients of my linear system are a sub 1 and b sub 1 for the first equation, a sub 2, b sub 2 for the second equation. Sorry to use some new notation on you, but it's easier to explain this way. So there's a system of two equations, two unknowns. What's the game? It's the usual game. Find x and find y. The a's, the b's, and the c's would be given to you. They'd be numbers. Well, here's the answer. Bingo! The answer is explicitly given by Cramer's rule. X equals, here's what x is. It's a quotient. In the denominator is a 2-by-2 determinant, and I'm using that awkward notation of the vertical lines to indicate that it's a determinant. And it's the determinant of the coefficient matrix, A1, B1, A2, B2. So the denominator is pretty simple. It's the determinant of the coefficient matrix of the linear system. Now, what's the numerator? Well, the numerator is almost the same thing, except because you're finding x, the first variable, you replace the first column, which used to be A1, A2, you replace it with the right-hand side, C1, C2. So the first column is C1, C2, the second column is B1, B2. That's the value of x. It's a determinant divided by another determinant. Bingo, an explicit formula for x. And y looks almost the same. The denominator, again, is that determinant of the coefficient matrix. The numerator now is slightly different. Because y is the second variable, you replace the second column with C1, C2, and you keep the same first column, A1, A2. So y is also a quotient of two determinants. Let's illustrate this technique with an example, and then I'll ask you that question. Do you like this technique? All right. How about the linear system 4x minus 2y equals 10 and 3x minus 5y equals 11? Find x, find y. We've played this game before. Here's a new method. Kramer's rule. Set up those determinants. All right. The denominator will be the determinant of the coefficient matrix. So it's 4 minus 2, 3 minus 5. What's the numerator? Well, it's almost the same thing, except replace the first column by the right-hand side, 10, 11, and keep the same second column, minus 2, minus 5. And now calculate those 2 by 2 determinants. Well, the top one is plus 22, 11 times minus 2, but you subtract that, so it's plus 22, divided by 4 times minus 5 is minus 20 plus 6. And then simplify that, minus 28 over minus 14, that equals 2. So x is 2. And I found it explicitly. I didn't have to do any row operations, did I? How about the second unknown, y? Okay, the denominator is the same as we had before, but the numerator is different now. A1, A2 is the first column, and you replace the second column with the right-hand side, 10, 11, and now compute those determinants. Well, the bottom one's the same as before, minus 20 plus 6 or minus 14. The top one is 44 minus 30, or 14, and that answer is minus 1. So our final answer is 2 minus 1. What do you think? You like the method? Imagine you were solving a 10 by 10 linear system, 10 equations, 10 unknowns. Would you want to use Kramer's rule? Well, you'd have to calculate these determinants that are 10 by 10. Not very pleasant, is it? So in real life, nobody uses Kramer's rule anymore. I'm exaggerating. I actually know some people at the University of Florida that still use it. But computationally speaking, it's a very slow and inefficient method. Much better to use that Gaussian elimination process. In a sense, Kramer's rule is a theoretical tool. It's really nice that you have an explicit formula for x and y. X equals blah, y equals blah. But calculating those things can be quite difficult. All right, let's turn to another application. Stopping distance. You're driving a car at a certain speed and you put your foot on the brake. How long does it take to stop? Well, imagine you work for a testing company and you're testing automobiles and brake systems. And suppose you discover that if you're going 30 miles an hour, that it takes 55 feet to stop. And if you're going 40 miles an hour, it takes, say, 105 feet to stop. And if you're going 50 miles an hour, it takes even longer to stop, 188 feet. So basically, you run some experiments and you time people as they try to stop the car at various speeds. Now, again, this is pretty simple, but in real life, you would have maybe 1,000 pieces of data here. You would have all kinds of data. How could you get a handle on this data? Well, here's one way. We could fit a parabola to this data. And we've done fitting of parabolas before. And then why don't we use that parabola to predict how long it would take to stop if we were going 70 miles an hour. So we use the data from a lot of experiments to try to predict the outcome of a different experiment. This is a very common kind of engineering problem. So let's do it. Let's assume our parabola looks like they all do, ax squared plus bx plus c. We're trying to find a, b, and c, and we have some data here, don't we? We know that when we're going 30 miles an hour, when x is 30, the stopping distance is 55, so that gives rise to an equation, a times 30 squared plus b times 30 plus c equals 55. And then you plug in the second and third equations. You get a times 40 squared, b times 40 plus c equals 105, and finally a times 50 squared plus b times 50 plus c equals 188. So we have three equations, three unknowns. We've been here before. The equations are not quite as pleasant to work with. There's big numbers here. Let's put them in matrix notation. and I'll put the coefficient matrix and the right-hand side together, and it would be 930, 155. That's the first row. Then it's 1600, 41, 40, 1, and 105. And the third row is 2500, 50, 1, and 188. All right. We know how to do this. We solve the system. Trust me, you can row reduce this and solve it. I did this on my graphing utility, but you could do it by hand. It's not a very pleasant system to do by hand. The operations to eliminate the variables would be fairly unpleasant. You would enter fraction land, as I like to say. But here's the answer you get. A is 0.165, B is minus 6.55, and C is 103. So we have our parabola that fits the data. It's 0.165x squared minus 6.55x plus 103. That parabola satisfies the 3 data points that we were given. All right, what can you do with this? Well, if you want to know what happens when we're going 70 miles an hour, plug in x equals 70 into this equation for the parabola, and you get 453 feet. So, is that a realistic model? Well, we didn't have much data to work with, but I think you get the idea. Fitting curves to data is big business. If we had had 4 data points instead of 3, then we could have fit a cubic polynomial rather than a quadratic polynomial, etc. And you can fit higher degree polynomials if you have more data. And by the way, there's a whole world of fitting curves to data. Sometimes they use something called splines, cubic spline. That's a whole different topic, but the bottom line is fitting curves to data is big business. All right, let's move to computer graphics. Here's a very, very crude and brief introduction to how you might move images around a TV screen. And you can do this with matrix multiplication. Let me try to explain how this works. It's a neat application, I think, and when I teach a course called Linear Algebra at the University of Florida, I have students write programs using some of these ideas, and they'll take an image, say, of Snoopy, and they'll move it around the screen. They'll rotate it, or they'll flip it over, and things like this. And here's some of the basic ideas. Okay, we're going to consider points in the plane. But rather than write them as ordered pairs x, comma, y, I'm going to write them as a column, x, y. You'll see the reason because I have to multiply it by a matrix. And I have to have it as a matrix 2 by 1, 2 rows, 1 column. So the points are vertical matrices, x, y. And now I'm going to multiply x, y by the following 2 by 2 matrix, minus 1, 0, 0, 1. Let's see what happens when I do that. So take the matrix minus 1, 0, 0, 1 and multiply it by xy, where xy is written vertically, because now I'm allowed to multiply. Otherwise, I wouldn't be allowed to multiply. So what's the answer? Well, minus 1 times x is minus x, and then 1 times y is y. The answer is minus xy. Let's do a quick example to see it with a particular point. Suppose xy is 2, 3. Then it would be minus 1, 0, 0, 1 times 2, 3, and look what happens. The 2 turns into a minus 2, but the 3 stays where it is. So the point 2, 3 gets moved to the point minus 2, 3. That's a reflection across the y-axis. Here's a picture of what I'm talking about. There's the point 2, 3 in the first quadrant, and look at its image under this transformation being multiplied by that 2 by 2 matrix. Out comes minus 2, 3. And in general, xy goes to minus x, comma, y. Kind of neat, isn't it? How you can move points across the y-axis by a simple multiplication of a 2 by 2 matrix. All right, what do you think this matrix does to a point? 1, 0, 0, minus 1. Now the minus sign's in the second row. What do you think it's going to do? Well, let's try it out. Let's try multiplying that matrix times xy. Remember, xy is a point in the plane, but I'm writing it as a column matrix because I have to multiply. All right, and I get the answer x minus y. Or in particular, if I multiply by 2, 3, I get 2 minus 3. What happened to the point 2, 3? It went to 2 minus 3. It got flipped over the x-axis. Here's a picture of that situation. There's the point 2, 3, and its mirror image 2 minus 3 across the x-axis. And in general, xy goes to x minus y. Wow, okay, so you can see how you can move points various ways here. Let me show you another one. What does this do to a point? The matrix 2, 0, 0, 2. How does this change pixels on your TV screen? You have some pixels, say, at xy. What's the outcome after you multiply by this matrix? Well, I think you can see what's going to happen. You get 2x, 2y. It goes further away from the origin, doesn't it? For example, if I'm at the point 1, 1, and I multiply by 2, 0, 0, 2, I end up at 2, 2. I've moved further away. So I see I can make things move far away from the origin. And now you can imagine the following. You could do a series of these transformations. Multiply by one matrix and the point moves over here. Multiply by another matrix, then it moves over here. And you can move an image around by moving each point of that image. And that's sort of one of the basic ideas of moving things on a television screen. Let me challenge you with a more complicated transformation. The 2 by 2 matrix cosine theta minus sine theta, cosine theta. So this matrix, again, is a 2 by 2 matrix. And for a given theta value, an angle theta, compute the cosine and the sine and then fill in the matrix. What do you think this does to a point in the plane? And here's a hint. We're using trigonometry here, aren't we? And trigonometry deals with rotations, changing angles. It turns out that this kind of transformation will rotate a point around the origin an angle theta. It rotates it theta degrees around the origin. So that's really a neat transformation, I think. You know, it's one thing to flip it across the x-axis or across the y-axis, but rotating an image, that's kind of cool. And this is the transformation that does it. I invite you to plug in a value for theta and then multiply it by a point and see what happens. All right, good. I'd like to look at a little more complicated example. And this example is often called network analysis. This would come up if you were studying, say, the flow of water through a system of pipes, or you would look at the flow of traffic through a system of roads. And again, we'll have to focus on a very simple setup here, but the ideas would carry forth to a more complicated system. So what I'm going to describe is a certain traffic pattern. We're going to have 4 corners, and traffic is going to be coming into these corners and then going out. Here's the setup. It's kind of a complicated looking picture, I know, but let me try to explain what's happening. There are 4 dots here which indicate corners or where traffic is coming in and traffic is leaving. And up in the upper left-hand piece, you see that 300 cars are coming in, and then they divide into 2 different routes. X1 of them, so X1 is an unknown, that's how many cars go that way, and then X2 go down vertically. And then 200 cars enter down at the bottom, and they split into 2 pieces. part of them, x3 goes diagonally up and x5 goes straight through. And then we have some more flow patterns. 150 cars leave at the top route, 350 leave at the bottom, and the x4 flow is from the top to the bottom. So all these numbers, x1, x2, x3, x4, and x5, can vary depending on the time of day. I'm assuming these are one-way streets, but if they weren't, they might have a negative number, and that means traffic got reversed on it. But do notice the following. How many cars are entering this system of traffic? 500, 300 plus 200, and 500 are coming out. So at least the same number come in as come out. So here's the game. We have this flow around this traffic pattern, and we're trying to discover the values of x1, x2, x3, x4, and x5. We want to know how much traffic is going along each road, okay? And then we'll discover that there's an infinite number of solutions to that question. So we'll finally specify certain specific values. We'll say that x5 is 350 and x3 is 50. And you can control that by stoplights and things like that. All right, so let's solve the problem. Let's look at the upper left-hand corner there where 300 come in and x1 plus x2 cars come out. That gives rise to a linear equation. x1 plus x2 equals 300. In other words, the amount of cars that come in has to equal the amount of cars that leave. So the first equation is x1 plus x2 equals 300. Now let's look at the upper right. x1 plus x3 are arriving. 150 plus x4 are leaving. That's our second equation. x1 plus x3 equals 150 plus x4. Let's look now at the lower left. 200 plus x2 are coming in, and x3 plus x5 are leaving. So x2 plus 200 equals x3 plus x5. And that can be rewritten a little bit. x2 minus x3 minus x5 equals minus 200. And finally, the fourth node, we have x5 and x4 coming in and 350 leaving, so the sum of x4 and x5 has to be 350. Okay, so by analyzing each node here, each corner, we discover that we get equations involving the flow variables x1 through x5. And we can set up a system of linear equations that represent these flow patterns. Here's the system of linear equations. There are 4 of them because there were 4 corners, and they involve 5 variables, don't they? x1 through x5. And then they have a right-hand side, those numbers. Here they are. x1 plus x2 equals 300. That was the first equation. And in matrix notation, you would write it as the first row of your matrix, 1, 1, 0, 0, 0, 300. The row corresponding to the second equation, it turns out to be 1, 0, 1, minus 1, 0, 150. The third equation, 0, 1, minus 1, 0, minus 1 equals minus 200. And the fourth equation, x4 plus x5 equals 350, corresponds to 0, 0, 0, 1, 1, and then 350. And I've put that dotted line there to really indicate that the final column is the column of the constant terms. All right, we've been here before. Here's a linear system. 4 equations, 5 unknowns. Is there a solution? How many solutions are there? How do you find them? Well, you find them by row reduction, by Gaussian elimination. You do that, so same old operations where you eliminate variables and get it into a final form where you can read off the answer. Now, I could have done this by hand, but I'll be honest with you. I put this into my graphing calculator, and I put it in as the giant matrix, and it spit out the following solution, a new matrix that is sort of in final form. They actually call this reduced row echelon form. That's a technical term for saying you finished solving the system. And here it is. The first row is 10101, and then the right-hand side is 500. Then it's 0, 1, minus 1, 0, minus 1, and the right-hand side is minus 200. 0, 0, 0, 1, 1, and that's 350. And it's kind of amazing. The fourth row is all zeros. So one of the equations kind of disappears, and we're left with just 3 equations. So we now have the resulting matrix after doing Gaussian elimination. I admit I cheated. I used my calculator, but I got that result. Let's translate back to equations. Well, the first equation would be x1 plus x3 plus x5 equals 500, x2 minus x3 minus x5 equals minus 200, and x4 plus x5 equals 350. All right, there are an infinite number of solutions here. There's a lot of solutions. Let me show you how you write this, how you describe this infinite number of solutions. It's very similar to what we did in a previous lecture, but it's more complicated here. Well, you would expect it to be more complicated. We're doing a real-life problem now, an application, so the computations can be more difficult. But here's how you describe it. You kind of work backwards. Look at that third equation. x4 plus x5 equals 350. Think of x5 as being the independent variable. I like to use the word free variable. x5 can be anything it wants. But once you've selected x5, x4 is determined. It's going to be 350 minus x5. So here's how we write it. x5 can be anything it wants to be. Call it t. Call it t. And once you've determined that value, x4 is 350 minus t. Now look at x3. It's also a free variable. It can be anything it wants to be. So let's call it r. And now x2 is determined. x2 is equal to x3 plus x5 minus 200, so it's r plus t minus 200. And now finally we arrive at x1, and x1 is 500 minus x3 minus x5, so it's 500 minus r minus t. That's complicated. That's tough to do. Identify free variables that can be any real number, and then the other variables are forced upon you once you select those values for the free variables. And in this case, we have 2 free variables, don't we? T and R. So if you were to analyze this traffic pattern, you could give a value for T and a value for R, and that would determine all the other values, wouldn't it? In particular, in this problem, we asked the question, what's the flow if x5 is 350, that's T, and x3 is 50, that's R. So if x5 is 350, that's the t value, and x3 is 50, that's the r value, then all the other values are forced upon us. We have no choices anymore. x4 will be 350 minus t, or 0. Wow, that road has no traffic now under this scenario. x2 is r plus t minus 200. That's 350 plus 50 minus 200. 400 minus 200 is 200 cars. And then x1 is 500 minus r minus t. That comes out to be 100. Here's the resulting model of the traffic flow given those further restrictions that x3 is 50 and x5 was 350. And notice what happens here. All the other values are now forced upon us. And I thought it kind of interesting that the X4 road suddenly got closed off. No traffic on that road. Maybe they did some construction on it and had a detour. But still, 500 cars come in, 500 cars leave, and you have a very particular traffic flow within that scenario. So what have we seen? We've seen that these systems arise in lots of real-life situations. The system we just had there, I solved it with a calculator, and it was a pretty small system. In real life, you can have systems with thousands of equations and thousands of unknowns. I probably never told you this before, but I used to work for NASA a few summers, and we routinely solved systems of equations with well over 1,000 variables and 1,000 unknowns, routinely. Of course, we did it with computers. So in real life, we were modeling airflow, and in real life, these kinds of things come up all the time. So I hope you have a taste now of how linear systems can arise in real-life applications, how matrices can be used to help solve those systems, how determinants can be used to solve systems, although I think we noticed that was not a great method, that Cramer's rule. Well, now we're going to switch gears completely. We're going to talk about a whole new set of topics called conic sections. This is great stuff and crucial for calculus courses. We're getting right back now to mainstream calculus applications. This is a pre-calculus topic that occurs all the time in calculus. We'll talk about circles, parabolas, ellipses, and hyperbolas. In particular, planetary motion. The planets go around the sun in elliptical orbits, one of the first applications of calculus. So I look forward to seeing you next time when we begin our study of conic sections. Thank you very much.